Welcome. What you are about to watch is not science fiction, and it is not folklore. It is a serious investigation into one of history's most compelling unresolved questions: the mystery of the interstellar object Borisov, what Oumuamua's companion told us about interstellar visitors. Across the world, in universities, research institutes, and field excavations, serious scholars are wrestling with evidence that does not fit the accepted story. Evidence that has been documented, measured, and peer-reviewed, and that still has no satisfying conventional explanation. We are going to look at that evidence carefully, without prejudice in either direction. Not dismissing what is extraordinary, but not accepting it without scrutiny either. The truth, as always, is in the details. In October 2019, 2 years after Oumuamua became the first interstellar object ever detected passing through our solar system, amateur astronomer Gennadiy Borisov of Crimea noticed a fuzzy comet-like object moving across the sky at an angle no object bound to the sun could achieve. C/2019 Q4 Borisov was an interstellar comet, the second object from beyond our solar system ever detected, and the first one that arrived with enough notice for the astronomical community to observe it in detail across multiple telescopes before it disappeared back into interstellar space. Unlike the cigar-shaped, famously cometless Oumuamua, Borisov was unmistakably a comet. It had a coma of gas and dust, a tail, and a composition that turned out to be both reassuringly familiar and slightly strange. The story of Borisov is in some ways the opposite of the Oumuamua story. Oumuamua baffled astronomers because it behaved strangely. It had no detectable coma or tail, despite being close to the sun. Yet it accelerated away from the sun in a manner inconsistent with gravity alone. These anomalies fueled intense speculation, including, most famously, Avi Loeb's proposal that Oumuamua might be an artifact of alien technology. Borisov, by contrast, was instantly recognizable. It was a comet, but a comet from another star system, a comet that formed around another star, possibly billions of years ago, and had been traveling through interstellar space for an unknown period before entering our solar system. The spectroscopic analysis of Borisov's composition revealed it was chemically similar to comets in our own solar system, but not identical, and the differences are telling. The detection of Borisov, coming just 2 years after Oumuamua, has led astronomers to estimate that interstellar objects passing through the solar system are much more common than previously thought, perhaps one per year at detectable sizes. Most of the time, they pass without anyone noticing. The universe, it turns out, is full of interstellar travelers, rocks, comets, and possibly other things moving between star systems on journeys that take millions or billions of years. Borisov was one of these travelers. It visited, we watched, we measured its chemistry, and it left. Where it came from and where it is going remain unknown. But it has told us something profound. The solar systems of the universe are not isolated. They are connected by an invisible highway of material moving constantly between the stars. This is where our investigation begins. Stay with us, because the further we go into the evidence, the more extraordinary it becomes. The story you think you know is only the surface. Beneath it lies something far more remarkable. Let us begin. Before we go further, if you are finding this investigation compelling, please take a moment right now to like this video, drop a comment below with your thoughts, and share it with someone who loves a good historical mystery. If you are watching on YouTube, hit subscribe and tap the bell icon so you never miss a new episode. If you found us through Facebook, tap follow on our page. It takes just a few seconds, and it genuinely helps us keep making these documentaries. Now, let us get back to the investigation. Before we examine the specific evidence, we need to step back and understand the context. This case does not exist in isolation. It sits within the expanding frontier of unexplained cosmic phenomena, and to properly evaluate what we are looking at, we need to understand the broader picture that surrounds it. Space is not quiet. The universe is filled with electromagnetic signals, from the cosmic microwave background radiation left over from the Big Bang to the steady roar of stellar activity at every wavelength of the electromagnetic spectrum. Against this noise, radio astronomers look for something specific, signals that are narrowband, repeating, and structured, the signatures of intelligence rather than nature. Natural processes tend to produce broadband emissions spread across many frequencies. A narrowband signal at a single precise frequency suggests something deliberately tuned, and deliberate tuning implies a tuner. The search for such signals has been ongoing since 1960, when Frank Drake pointed a radio telescope at two nearby stars and listened. In the 60-plus years since, the instrumentation has grown enormously in sensitivity, and the sky survey coverage has expanded from a handful of stars to millions. The verdict so far is ambiguous. No confirmed, repeating signal from an extraterrestrial intelligence has been received, but several anomalous signals have been detected, investigated, and not definitively explained, including at least one that, had it been received today, would meet every criterion the scientific community had previously agreed would constitute first contact. The silence of the cosmos is not total. It is merely inscrutable. This context matters because it tells us something important. What we are about to investigate is not an isolated curiosity. It is part of a pattern that researchers in multiple fields have been independently documenting for decades. And patterns, in science, demand explanation. With that foundation in place, let us now turn to the specific case at hand. Now we reach the heart of the matter. The core evidence surrounding the Interstellar Object Borisov, what Oumuamua's companion told us about interstellar visitors, is more extensive, more verified, and more troubling for conventional explanations than most people realize. Let us walk through it systematically, fact by fact, and allow the evidence to speak for itself. We are not going to speculate here. Every point that follows is documented in peer-reviewed publications, official archaeological records, or government archives that are publicly accessible. The question is not whether these facts are real. The question is what they mean. Consider this first extraordinary detail. C/2019 Q4 Borisov was discovered on August 30, 2019 by Ukrainian amateur astronomer Gennadiy Borisov using a custom-built 0.65-meter telescope at his observatory in Crimea. Borisov noticed the object's unusual trajectory. Its orbit had a hyperbolic eccentricity of approximately 3.36 compared to the maximum eccentricity of 1.0 for objects on the boundary of solar system escape velocity, which immediately suggested an interstellar origin. The object was confirmed as interstellar by multiple independent orbital determinations within a week of discovery. The closest approach to the Sun, perihelion, occurred on December 8, 2019, at a distance of approximately 2 astronomical units. This single data point, if taken in isolation, might be set aside. Anomalies happen, instruments malfunction, researchers make mistakes. But as we continue, you will see that this is not an isolated anomaly. It is part of a consistent and documented pattern. But that is only the beginning. Researchers also discovered spectroscopic analysis of Borisov's coma, the cloud of gas and dust surrounding the comet's nucleus, was conducted by multiple teams and published in several papers in 2020. The coma chemistry revealed carbon monoxide, Co, at approximately twice the concentration found in most solar system comets. Oxygen in the form of O2, molecular oxygen, also detected in comet 67P/Churyumov-Gerasimenko, water ice identified in the nucleus, and silicate and carbonaceous dust particles with optical properties similar to those of solar system comets. The CO enrichment is the most notable compositional difference from typical solar system comets, possibly reflecting a different formation environment around the parent star. Now, a skeptic might propose an alternative explanation for this, and that is entirely reasonable. We should always test alternative explanations before accepting extraordinary ones. The problem is that the alternative explanations, when examined carefully, create more problems than they solve. The mystery deepens when we examine. The nucleus of Borisov is estimated to be approximately 0.4-0.9 kilometers in diameter based on optical brightness measurements. This makes it significantly smaller than the comets typically studied in detail. Comet 67P, visited by the Rosetta spacecraft, is approximately 4 kilometers. The small nucleus size, combined with the high activity level, large coma relative to the nucleus, suggests either that the nucleus is very volatile rich, or that the tidal stresses of its interstellar journey and solar flyby have begun to fragment the nucleus. High-resolution Hubble observations in late 2019 showed what appeared to be enhanced dust emission consistent with fragmentation of the nucleus. This is where the conventional account begins to strain. Each individual fact might be dismissed or minimized in isolation, but the cumulative weight of the evidence is another matter entirely. Perhaps most remarkable of all, Borisov's trajectory reconstruction, working backward from the observed path, indicates that it most likely originated in the vicinity of the Kruger-60 binary star system, located approximately 13 light-years from Earth in the constellation Cepheus. The object appears to have left the Kruger-60 system approximately 1 million years ago, based on the backward extrapolated trajectory, though the precision of this estimate is limited. If this origin is confirmed, Borisov would be a comet that formed around a binary star system, suggesting that planet and comet formation around binary stars can produce objects with compositions similar to those formed around single stars like the Sun. Researchers who have examined this evidence have described it as genuinely difficult to explain within the accepted framework. These are not fringe commentators. They are credentialed academics publishing in mainstream journals, raising questions that the field has not yet satisfactorily answered. Then there is the matter of the implication of detecting 2 interstellar objects within 2 years, Oumuamua in 2017 and Borisov in 2019, is that interstellar objects are far more common in the solar system than anyone expected. Statistical estimates based on the detection rate suggest that approximately 1 interstellar object larger than 100 meters passes through the inner solar system every year, and that at any given time, there may be 1 interstellar comet within the orbit of Neptune. The vast majority of these pass undetected because current survey telescopes are not sensitive enough to find them. The upcoming Rubin Observatory, scheduled to begin full science operations in the late 2020s, is expected to detect dozens of interstellar objects per year. What makes this particularly significant is its independence from the previous points. This is not a case of one theory requiring another. These are separate lines of evidence converging on the same uncomfortable conclusion. Adding to the enigma is this finding: the detection of CO at twice normal levels in Borisov is scientifically significant because CO-rich comets on Earth are associated with formation in the colder outer regions of protoplanetary disks, the region beyond the CO snowline, where temperatures are low enough for CO to condense into ice. If Borisov formed in the outer region of its parent stellar system, it represents material from an environment analogous to the cold outer solar system, beyond the orbit of Saturn, preserved in interstellar space for possibly billions of years, and delivered to our own solar system for study. The CO enrichment may also reflect that the parent star is a cooler, dimmer star than the Sun, with a different temperature profile in its protoplanetary disk. Taken together, these facts form a pattern that cannot be explained by coincidence, misidentification, or methodological error. Each piece of evidence has been examined by skeptics. Each has been subjected to alternative explanations. And in each case, the alternative explanation falls short of accounting for everything that has been documented. We are left with a body of evidence that demands explanation and an accepted narrative that does not provide one. This is where serious inquiry begins. Now that we have established the evidence, we need to examine the theories that researchers have proposed to explain the interstellar object Borisov, what Oumuamua's companion told us about interstellar visitors. This is where the debate becomes most intense, because the theories reflect not just different interpretations of the same evidence, but fundamentally different assumptions about what is possible and what the past looked like. Understanding these theories is not just an academic exercise. Each one has been championed by serious researchers with genuine credentials, and each one captures something that the others miss. The truth, if it is ever established, will likely draw on elements of several. The first major explanation proposed by researchers holds that the universal cometary chemistry theory holds that Borisov's broadly solar system-like composition indicates that comet formation processes are universal, that the physical and chemical conditions that produce comets around our sun produce comets with similar compositions around other stars. The slight differences in CO abundance and some other trace species are interpreted as reflecting normal variation in protoplanetary disk conditions rather than fundamentally different chemistry. Under this view, Borisov tells us that the building blocks of life, complex organic molecules, water, ice, that comets deliver to young planets are probably available throughout the galaxy, wherever stars and their planets form. This interpretation has significant academic support and is backed by substantial evidence, but it is not without problems. Critics point out that it requires assumptions that go beyond what the evidence strictly supports, and that key predictions of this theory have not been confirmed by subsequent research. It remains contested, and the contest is productive. A rival school of thought argues that the stellar environment differentiation theory argues that the differences between Borisov's composition and typical solar system comets reflect systematically different protoplanetary disk conditions around the parent star, possibly a cooler star, a different carbon-to-oxygen ratio in the disk, or different disk structure. Under this model, interstellar comets can serve as probes of the formation environments of their parent stellar systems, much as meteorites in our own solar system preserve chemical records of the early solar nebula. Detailed comparison of multiple interstellar objects' compositions would, in principle, allow a survey of protoplanetary disk chemistry across multiple stellar systems. This theory is controversial, and deliberately so. Its proponents argue that the evidence demands an explanation outside the conventional framework. Critics counter that extraordinary claims require extraordinary evidence, and that the evidence presented, while suggestive, does not yet meet that standard. The debate continues in peer-reviewed literature. Perhaps the most unconventional theory suggests that the fragmented planetesimal theory proposes that Borisov was not a comet in the conventional sense, but rather a fragment of a larger icy body that was disrupted in its home system, possibly by a planetary collision, a stellar tidal encounter, or the breakup of a larger interstellar comet during a previous close stellar encounter. If the CO enrichment reflects exposure of fresh, unprocessed interior material from such a disruption, Borisov's composition might reflect the interior chemistry of Kuiper belt-equivalent objects in its parent system rather than a typical cometary surface. This could explain anomalous aspects of its composition without invoking unusual formation conditions. What is striking about this debate is not merely that experts disagree. That is normal and healthy in science. What is striking is the quality of the disagreement. Serious researchers working from the same body of evidence reaching genuinely different conclusions. That level of fundamental disagreement, when it persists over decades, is a signal that something important has not yet been understood. The question is not which of these theories is right. The question is whether any of them is right, or whether the truth is something that none of the current frameworks has yet been able to capture. The case surrounding the interstellar object Borisov, what Oumuamua's companion told us about interstellar visitors, does not rest on speculation alone. What distinguishes this investigation from pure mythology is the existence of documented, physical, verifiable evidence, material that has been examined by credentialed researchers and whose authenticity is not seriously disputed. What is disputed is its interpretation. Let us review the most significant documented evidence as objectively as possible. We are not going to cherry-pick the data that supports a preferred conclusion. We are going to lay out what exists and let you draw your own assessment. Physical evidence supporting this account includes the hyperbolic orbit with eccentricity 3.36 is the definitive evidence for Borisov's interstellar origin. An object bound to the solar system can have at most an eccentricity of slightly above 1, a parabolic escape trajectory. Eccentricities above 1 indicate excess velocity relative to the solar system that must have been acquired outside the solar system. Borisov's eccentricity of 3.36, measured from dozens of independent astrometric observations, is so far above the solar-bound threshold that even extreme measurement error could not change the conclusion. The interstellar origin is certain. This evidence has been subjected to independent verification. Skeptics have examined it. Alternative explanations have been proposed and tested. The data remains. The question of what it means remains open. Investigators have documented the spectroscopic detection of CO at twice the typical solar system comet abundance was published by multiple independent groups using different instruments and techniques, including the Oumuamua radio telescope, which detected CO directly in the microwave band, the VLT and Gemini telescopes, which detected it in the optical and HSD ultraviolet spectroscopy. The consistency of the CO measurement across multiple platforms and wavelengths confirms that the elevated CO is a real compositional characteristic of Borisov rather than an instrumental artifact. This represents the first direct measurement of the chemical composition of a comet from outside our solar system. This evidence has been subjected to independent verification. Skeptics have examined it. Alternative explanations have been proposed and tested. The data remains. The question of what it means remains open. On-site analysis revealed the Hubble Space Telescope's monitoring of Borisov over 5 months, September 2019 to January 2020, tracked the evolution of the comet's coma and tail with spatial resolution unachievable from the ground. The Hubble images showed the coma expanding at a rate consistent with active outgassing of volatiles heated by the sun, confirming that the comet was behaving physically like solar system comets. The images also showed signs of nucleus fragmentation in late 2019, possibly triggered by the thermal and tidal stress of the solar encounter. The eventual fragmentation of the nucleus, confirmed in 2020, means Borisov left the solar system as fragments rather than as a single intact body, scattering remnants of an interstellar comet across the inner solar system. This evidence has been subjected to independent verification. Skeptics have examined it. Alternative explanations have been proposed and tested. The data remains. The question of what it means remains open. Each individual piece of evidence might, in principle, be explained away. A single anomalous artifact might be misidentified. A single anomalous date might reflect contamination. A single anomalous eyewitness account might reflect misperception. The question is whether all of the evidence can be explained away, and whether the explanations required are more or less plausible than the evidence itself. When multiple independent lines of inquiry converge on the same conclusion, that convergence is the most powerful signal in empirical science. And that is exactly what we are seeing here. We have examined the history, the evidence, and the theories surrounding the interstellar object Borisov, what Oumuamua's companion told us about interstellar visitors. Now, we need to ask the question that is sometimes overlooked in discussions of ancient mysteries. Why does this matter? What does it mean for us today? It would be easy to file this away as an interesting historical curiosity, a puzzle from a distant past with no bearing on our present lives. That would be a fundamental mistake. The questions raised by this case touch on issues that are directly relevant to who we are, where we came from, and what the human story actually looks like before the period covered by conventional history. Borisov exited the inner solar system in 2020 and is now receding from both the Sun and Earth at high velocity, heading into interstellar space in the direction of the Libra constellation. It will leave the solar system permanently and is already too faint for most telescopes to track. The scientific data collected during its relatively brief transit through the inner solar system, approximately 4 months of intensive monitoring, is still being analyzed and published. The legacy of Borisov, together with Oumuamua, has fundamentally changed how astronomers think about interstellar objects and their role in connecting star systems. The Rubin Observatory Legacy Survey of Space and Time, expected to begin full operations by 2025, will survey the sky with sufficient depth and cadence to detect interstellar objects far more frequently than current surveys. Theorists predict that Rubin will discover dozens of interstellar objects per decade, allowing the compositions of these visitors from other star systems to be systematically characterized and compared. What was once a theoretical concept, interstellar debris connecting the galaxy's stellar systems, has become an observational reality. The solar system is not a closed system, and the universe is more interconnected than we knew. Furthermore, the tools available to investigate these questions are advancing rapidly. Satellite imaging, ground-penetrating radar, ancient DNA analysis, isotopic tracing, and deep-sea sonar are all providing capabilities that previous generations of researchers could only dream of. Cases that were genuinely unresolvable 10 years ago are now open to new analysis, and the findings, consistently, are expanding rather than contracting the mystery. The investigation continues. New discoveries are being made. New analyses are being published. New voices are entering the conversation from disciplines that were not previously part of the discussion. The answers, when they come, and they will come, will not merely solve a historical puzzle. They will force a fundamental revision of assumptions that underpin our entire understanding of human history and human potential. We have now walked through the complete case of the interstellar object Borisov, what Oumuamua's companion told us about interstellar visitors, from the historical R, echoed through the physical evidence, across the competing theories, and into the modern significance of what remains unresolved. What the story of Borisov ultimately reveals is not just a historical puzzle. It is a mirror. It reflects our assumptions back at us, our assumptions about what ancient people were capable of, about how knowledge is gained and lost across the centuries, and about the relationship between what we know and what we merely think we know. The evidence presented in this documentary is real. The questions it raises are genuine. The debate among researchers is ongoing, and that is healthy. Science is not a set of conclusions. It is a process. And the process requires that we remain open to evidence that challenges what we thought we knew, however uncomfortable that challenge might be. If you came to this documentary as a skeptic, we hope the evidence gave you something to think about. If you came as a true believer, we hope the critical examination gave you a more nuanced picture. The truth, as always, lies in the evidence, not in what we want to be true. Thank you for watching. If this investigation sparked your curiosity, please help us reach more people. If you are watching on YouTube, subscribe to the channel and hit the notification bell so you never miss a new documentary. If you are watching on Facebook, tap the follow button on our page to stay connected. We publish new documentaries every week, covering the full range of historical mysteries that the mainstream has not yet adequately explained. Leave a comment telling us which case you want us to investigate next. The conversation continues. The investigation never ends.